Okay, so last video for class 21, I totally spaced and forgot, or I flipped past a page that I wanted to have. So before I do the example, I just want to conclude on what we had here for major losses is the main equation that we want to have. So we could write it either as a head loss or a pressure loss, but the traditional way to do this is to write for a head loss, which will be Darcy friction factor times the length over the diameter times v squared over 2g. All right, so that's what we consider the major head loss. If we want it instead by pressure, of course, in a major pressure drop, we would take F times L over D and then take rho v squared over 2. There's really not that much difference between these two things. So just remember that we could get head by dividing pressure by specific weight. So that just, we got rid of the density and there's now a G in there. So that's just the big difference in there. But it's an interesting, or maybe not interesting, it's a important way to go about thinking about pressure drop calculations is to do it in terms of head. Also wanted to point out in here, right, that we can do this numerically. We don't have to use the Moody diagram. So that's going to really help us when we go to make a spreadsheet. And I'm going to do have you make a similar spreadsheet to the one that I made, and you're able to do pressure drop and piping calculations using that. It's very convenient. So let's point out first that we have, we already knew this Darcy friction factor from here. This is an approximate method down here to try to get the Darcy friction factor from an equation. It is probably 1% of deviation from the actual one. There's a couple other equations that are in the book that you can use. One's called the Colebrook equation, but unfortunately, you have to do an iterative process to get it to work. And there's also another one that I hadn't seen before. I think it's called the Halland. No, or maybe the Church. I think this is the Halland. Yeah, this is the quote unquote HAALAND equation right here. There's also one called the Churchill equation, but it's a longer process, a series of equations. But you definitely get a better overall result most of the time than you do by trying to get it off of the graph. But you do need to practice getting off the graph because you might have a final exam, a problem where you have to use it. So just be able, when you go to practice it, you for exams, use the Moody diagram. All right, so let's go and do an example. And I picked out, or I wrote, I'm not sure. I might have written this. I might have found it. I don't know. So we want to estimate the head loss and pressure drop, and then the pump power required between stations on the Alaskan pipeline. And this is, if you recall the recent Homework 9, you know that I like this type of thing, right? Because there's a lot of practical sort of like, I wonder how much kind of that type of problem. We know the distance of the pipeline is 800 miles long, and we know that it has pumping stations. It's got 12, so it's got an average distance between them is like 66.6 miles or 352,000 feet. The pipe diameter is typically 4 feet in diameter, the big pipe. And the flow is something like 2.14 million barrels per day, which you could turn into 139 cubic feet per second. This is crude oil, and they need to heat it up to 140 degrees Fahrenheit in order to pump it, or to pump it efficiently. And at that temperature, it's got a specific gravity of 0.876, the density, of 1.7 slugs per cubic foot, and a viscosity of 7.8 e to the minus 5 pounds/second per foot squared. And we can assume that this is steel pipe at 0.0015. So we want to estimate the head loss, the pressure drop, and the pump power between stations. And by the way, in the real world, according to Wikipedia, every station has 4 13,500 horsepower pumps, and they usually use 3 operating at a time. So this is kind of an important, interesting thing to take a look at. This is big. So let's get the velocity, right? So the velocity is going to be the volume flow rate divided by the area. So 139 cubic feet per second. And we have pi over 4, and there's 4 feet. So we get 11.07 feet per second. So our first thing to find is the Reynolds number. So take the density, velocity, diameter, and viscosity. So our density was 101.70. Velocity we just found. Diameter is 4, and viscosity is 7.84 e to the minus 5. And you get 960,000. So let's take that 960,000 and take the log of base 10, so it's going to be 10 to the 5.98. And of course, it's almost a million, so that makes sense right there. So maybe we want to go and try to look this up. Instead of trying to look well, like I said, I've decided to do it both ways. So here is about where we are, right in there. Oh, we need the roughness too. I'm sorry. Let's see. Let's get the roughness. The roughness is going to be, we decided to go 0.00015 and divided it by 4 feet. It's going to be a really small number. 0.0000375 is the answer. So that's pretty low on this right here, right? So we have 1, 2, 3, 4, right? So, but we're coming up, right? So what do we have? Let me see. Did I mess this up before? Let me take a look. I marked it up. Yeah, so it's somewhere in between here and here. So you kind of like, you have to kind of like draw like kind of a curve, kind of matching line, approximating where you are between there or one in here, because it's somewhere in there, and kind of comes up like right into there, right? So somewhere like right in there, and then looking in between these, it's sort of this is a skill set that you have to develop to like look and maybe try to find, I don't know, do your best guess somewhere like right in there, and then counting these up, we could see that we go by these increments right here. 0.01 is right there, and 0.02 is right here. So here's the midpoint, 0.015. So here must be 0.011, 0.012, 0.013, 0.014. So I'm going to say that this is 0.012, 0.013, 0.0135. How did I do? 0.0, no, 0.011, 0.012. So 0.0125 is going to be there. All right. So hopefully maybe you could 0.0125. Let's go approximately. But we do have an equation for this. So let's try out that equation instead. Right. So we can see this is 1 over the square root. So that would be the same thing as going F is equal to minus 1.8 times the log. I like to go capital LOG there. And we're going to have this roughness ratio. We already have that somewhere, right? We're at 0.1234 and then 375. and divide it by 3.7 and raise it to the 1.11 and then add 6.9 divided by 960,000 and close that bracket and then close that parentheses. And this negative, by the way, these are really small numbers, going to end up negative, so that negative is going to go away. And this is going to be to the minus 2, right? Because this was square rooted, so we got to square this, and it was also 1 over it. So that's where the minus is right there. And if I do that, I end up getting 0.01236 for 4 sig figs. So you see that wasn't terribly bad. Wasn't a terribly bad thing to do it by the graph, but you just had to be really careful when doing it on there. So the head loss, and we're going to call this major, it's going to be equal to F times L over D times V squared over 2G. We had 0.01236. I'm going to go ahead and use the one from the equation, which is also an estimate. I mean, both of those are estimates, right? The length of the pipe was 352,000 feet, and the diameter is 4. The velocity is 11.07, and that's squared, and divided by 2. And we're using US units or British gravitational 32.2. And what we end up finding is we get a 2,069 feet of head loss. And trying to get our head around that, and no pun intended. Let's find out what the equivalent of the piping loss is going to be. And that's just going to be gamma times the head loss, or we don't know the specific weight, but we do know the specific gravity. So we can always just multiply the specific gravity, 876, times the specific weight of water, 62.4, right? And that together gets us the specific weight of that oil, crude oil. And then times that 2,069. And might as well divide this by the 144. So that we get it into PSI at 795 PSI. So that's got to be at least what that pump has to have as a discharge pressure. And in terms of power that it'll have to have, this pump hydraulic power, we're going to take that head loss. All right, because we're ignoring all the other Bernoulli things that we have to do, but this is such a huge amount. The head loss is way larger than anything else. We're going to use that head times the specific weight times the volumetric flow rate. We know that that's what power is going to be in a pump. So we have 2,069 feet. Once again, we'll do the 0.876 times the 62.4 to get the specific weight. And then the volumetric flow rate was provided 139 cubic feet per second. And we might as well divide by our 550, because all of this is going to get foot-pounds per second, so we want to turn it into horsepower. And what we find is we get 28,910 horsepower, right? But compare that to the real world and say, is that a reasonable amount, right? That's a great question. Is it a reasonable amount? Well, let's just say you take 3 pumps, and by the way, this is hydraulic power. This doesn't account for the inefficiency of the pump or the inefficiency of the motor. And by the way, it's not going to be an electric motor. It's going to be a big diesel, probably engine, a big engine that's doing this, and there's going to be one at every a group of these at every pumping station. But if you take 3 times your 13,500 horsepower, you get 40,500 horsepower, and perhaps that's enough to be able to. You better be enough to be able to overcome the inefficiencies of the pumps and the inefficiency of the engine. Of course, this is what the rated power is, so that's totally fine. But just imagine that takes a lot of energy to be able to get this oil from here, and every one of these is a pumping station to move that stuff along. So that is a lot of effort. So they must be very motivated to be able to get this Alaskan pipeline. So there you go. That was another example, and I thought it was a pretty cool real world example because you get the right actual numbers, and then you actually have something to compare it against. So ta-da, that's the end of class 21.